Okay, again, we'll just do this quick, and I'm going to ask you a series of questions over here.
Yep.
Okay, all right. So again, this is VP or V positive. We got VN and V negative. Okay. What is VP here? Yes, folks. VP is going to be VS. We know that VP equals to VN, and because VP equals to VS, so I can also write it down over here. What is VN here? What is VN here? You have V out here, this V out. Notice here in a buffer voltage follower, and you'll know why it's called voltage follower now. There's no beta factor here. It's eliminated. It's just a simple wire which is hooked up to negative terminal of the amplifier. So what is going to be VN? V out, correct? Correct. Now, if VN is equals to V out, and because VN is equals to VPS, VP equals to VS, then I can also say this is also equals to V naught, correct? We know A is equals to V naught output over input, VS. If V naught and VS both are same, then what would be the gain? 1, correct? Right? But okay, we got it. But what is the point of using this operational amplifier in this configuration when I am supplying something like this, and also at the output getting something like this same? There's no amplification, there's nothing. Why we are doing this? And basically it's, now you would know, it's doing the voltage follower, because whatever the voltage it would be, say it is 6 over here, 6 volt, so you get 6 volt over here, and then you will also get 6 volt over here, correct? Because VP and VN needs to be same, so that's why it's referred to as a voltage follower. Whatever the voltage is here, it'll just keep it constant, okay? It won't change. So that's one advantage. There's another advantage to it, and to understand that advantage, I want you to focus over here on this. This is also what we did and when we were trying to understand ideal sources versus practical sources. So say you have this series circuit right here. There's one component load connected in parallel over here, okay? At this node, whatever the voltage is also being fitted across this RL. So at this node, your, say, if I want to call it VL, this VL would be basically VS minus I, like current flowing in here is high, times R1, right? This resistor value right over here. The problem here, if this load is drawing more current, okay, or this more current, then if this number increases, then this whole term basically increases, right? So VL is going to be a small number, right? Ideally, we want it to be, VL close to VS, whatever we have over here, okay? We would want, this is a very small resistor, but if the more current is being drawn here, then it just messes up this equation over here, and then we get us VL as a smaller number. So this, if this is 16, you might get 9 or 10 or something like that, okay? So how do we go about that? Well, if I transform this circuit into something like this, okay, into something like this, same circuit, I got my VS here, okay, positive negative terminal, I got my R1 over here, I got my R2. This over here, I have removed my RL from here. Initially it was over here, correct? I have removed that RL. Instead of that, I am feeding this into the VP, the positive terminal of the amplifier. And what is this circuit right here? What is this whole thing? It's a buffer, right? This whole thing is a buffer. This whole thing, it's a buffer. Now, so what is the current flowing over here? What is the current flowing into the terminals of the, what was the golden rule? Remember, there were 2 golden rules. What was the second one? This I plus, this I minus, both are going to be 0. If no current is being drawn, then that means the voltage over here will always be constant, correct? It won't going to change. Doesn't matter how much current is being drawn over here by the resistive load, correct? Okay, all right. And Therefore, so say if you are getting 5 volt over here, so that means VP is going to be 5 volt. VP and VN both are same, you get 5 volt. So you get V out, what would be this voltage be? This voltage is going to be 5 volt, correct? Because this V out is just simply connected to the Vn. And if this is 5 volt, so you're basically getting 5 volt going through this resistive load. And because what is the output resistance of the ideal amplifier? 0 ohms. So this voltage is not going to decrease, that's regardless of how much being current is drawn by this load, because the output impedance of the operational amplifier is 0. So here it was messing up the voltage over here, right here, whereas it's constant and it's driving as much as current as it needs. Okay, so if you look at some of the motors that may be installed on pumps, they always have this buffer. Okay, so 3 types of amplifiers: non-inverting amplifier that we did earlier, the buffer, voltage follower, this one second, and the third one is basically the one that we did on Thursday. Okay, so you see how we applied golden rules, and they tell us, in this case, that no currents is flowing through to the input of the operational amplifier. Thus, the output voltage of the divider will not change when an op-amp buffer is attached. Okay, and also basically the op-amp observes its input voltage. The op-amp here basically observes the input voltage over here, and then replicates that same voltage over here. Okay. The voltage divider circuit and the load, so this circuit right here, this voltage divider circuit and the load over here, they are effectively isolated, and hence the name buffer for these kind of circuits. Okay, so that was the voltage buffer for you.